so I won't have room for us. So, any questions, you are more than welcome. And now, our next speaker is Dr. Gleb Fedorov, coming from MIPT. So, with the talk on superconducting quantum processors and simulators.
All right, thank you very much for inviting me, and this is a great pleasure for me to make a talk here in ITMO. And my speech is devoted to our recent experiments with the 5-qubit system based on Transmon. I will also give a brief introduction on the Josephson theory. Maybe it will be a bit redundant, but I think there are many people who are not familiar with the domain. Maybe still useful. All right, so this work was done in the collaboration with all members of our lab, both from the experimental part and from the fabrication as well. The laboratory, I can speak. Yes, so the plan of my talk is as follows. First, I will give a short introduction to the subject. Then, since the name of my presentation is the hardware for superconducting quantum deep learning or simulation, I will describe the hardware components of the experimental setup in maybe a bit more detail than elected, and show the current results with the 5-qubit chip we have. All right, so our lab is located in the suburbs of Moscow, in the north, in the city called Dolgoprodny. Here I have the picture of the fridge open, so Oleg wanted to show it, and I now can do that. So you can see here that when the fridge is open, it has several stages, several flanges, each of which has its own temperature. And here in the lowest, on the lowest, under the lowest stage, the samples are located. We have several magnetic shields which protect the qubits from the field of the Earth, basically, and from the field of the microwave components which are located on the bottom stage. But I will turn to this part in greater detail a few slides later. So what we mean when we talk about quantum simulator and compared with a quantum processor. The general idea behind the quantum processor is that you can have a quantum system based on well, any kind of physical realization of qubits, which can perform arbitrary quantum algorithms. There are not many quantum algorithms actually, which are theoretically proven to be competitive with the classical ones, but still your machine should be able to run arbitrary programs, arbitrary quantum circuits. And there is a huge problem for that, because real qubits have errors due to the coupling to the environment, because you have to have control over them, and you have to connect the processor to the external electronics. So you will inevitably introduce some decay channels into the system. And the way to cope with that is to develop the so-called error correction codes. When you make a redundant number of qubits, for example, 1,000 physical qubits for one logical qubit at an error rate of, I guess, 0.1%. And then you can get some kind of a digital quantum virtual processors that can run without errors. And this is a difficult task, because first of all, when you make a stabilized circuit, you will have to if you want to make gates on that, it will be tricky, because this system is protected, and you will have to invent some methods to perform, for example, two-qubit gates with the logical qubits. And maybe this is not the hardest part. The hardest part probably would be to make single qubit gates with the logical qubits. But all right, I think this the development of practical quantum computers would be not quite soon, as many expect. But still, how can we use maybe this impossibility to calculate, to simulate intermediate scale systems like containing hundreds of qubits on a classical machine? Well, one way is to use the quantum circuits, which could be error prone, but not as sensitive in terms of the results they yield to these errors. And they also may be optimized for a certain task. You don't have the aim to simulate, to be able to run any possible algorithm. So some kind of advantage may be found here, I believe, in coming years, 5 or 10. And considering the hardware for the quantum processors and quantum simulators in this sense, the hardware is pretty much the same, but for the processors, I believe one significant difference is that if you want to test some error correction codes, you need to implement fast feedback in the digital electronics at room temperature. So for the simulators, that might not be necessary. So in this sense, the simulators are also less difficult to develop.
So just a short question. So this part about error correction.
Yes.
So as far as I know, once you introduce additional qubits
yes.
To correct for errors, you also introduce some extra sources of noise. So you have this trade-off, and then to get some gain from these additional qubits, you need to go above certain threshold. So how close to this threshold are we current?
Well, I would say that adding qubits does not automatically mean that you are increasing errors for a single qubit gate, because you just make a block, for example, 1 qubit and the resonator, or okay, maybe a pair of qubits, and then you multiply this block, these blocks, and they do not significantly interfere with one block with the other. So you can scale the system this way, and not destroying the coherence of the blocks.
Okay, but then another question: are these single qubit operations enough to run?
Well, single qubit and 2 qubits.
Yeah, because you need 2 qubit gates.
Yeah. So why I'm confident in this, because recently Google has demonstrated that they can scale the logical circuits, the logical qubit. They not only do stabilization, they're not doing gates yet, but the stabilization does not deteriorate with increasing number of qubits, because recently it was questioned, but I think the work was published this summer. So the first experimental success in this direction. The threshold is only referring to one block. If of course when you increase the number of blocks, and this increase leads to a drop of the quality of the operations, that this will not make any sense, because there will not be a concept of threshold. But it looks like it will be possible in some way. Okay, so an interesting topic. Now it started from the variation of quantum eigensolvers, and now this is an idea when you have some kind of quantum circuit that you can run and tune the parameters of it, so that you can calculate some averages by measuring the state of the qubits afterwards. And this operation is done faster in the real quantum device than it can be done in the classical computer. So the generalization of this idea is that you have some circuit that prepares your quantum data set. There is a circuit that evaluates the quantum model. Then you can measure the qubits. Possibly you can run a classical neural network afterwards on the results. and evaluate the cost function and optimize the parameters of the whole both quantum and classical part to get, for example, some kind of classifier. So this is when this may be actually useful when the number of qubits starts to climb over, I think, 50. This device can't be simulated efficiently on a classical computer. So if you make a network, a quantum circuit with 100 of qubits, and you can tune the parameters of the gates, possibly you can get some kind of some kind of system that can solve some tasks. Maybe it will be more representative than a classical neural network, and so this is the final goal of building such kind of devices. So they can't be simulated on a classical computer, but they can be experimented with if you have a real chip. All right. Turning to the hardware components, I will briefly describe again the Josephson junction and the essential parameters of it. So here you can see the shadow evaporator Josephson junction with the schematic of the section of it shown here. And the current flows from the one shadow, which is light gray, to the other one, which is gray, through an oxide barrier. And the current flow is described by the Josephson equations, which are known for more than let's see, from 1962 actually. And yeah, the equations read that the current will be proportional to the phase difference, the superconducting phase of the shores, the junction, and the voltage would be proportional to the time derivative of the phase. And actually, this equation implies, or you can imagine that the Josephson junction can be treated like an inductance. So the inductive energy of such inductance equivalent one would be described by this cosine function, and thus we can talk about an effective particle in a cosine potential. If we look at this in the quantum domain, for example, let's remind ourselves about the quantum harmonic oscillator. So you make a circuit, you quantize it just as you do with the mechanical oscillator, and you get an infinite ladder of energy levels, which are separated by h bar omega r. So I think this should be familiar. And when you replace the inductance by the Josephson junction, it actually, when the capacitance is large, you will have a slight change in the lowest two levels, and more and more strong, more significant change in higher line layers due to the change of the potential from the parabolic to the cosine one that I have shown on the previous slide. So the Hamiltonian for this system, accurately it is shown here, but you can make an approximation and imagine that the Transmon is in its several lowest levels just a non-harmonic oscillator with the fourth order nonlinearity characterized by the coefficient alpha. So of course this only valid for lowest, I believe it depends on the unharmonicity, but for experimental parameters we can talk about say 5 or 6 lowest line levels, because levels, because otherwise well, the higher energy levels will become again the same as for the charge qubit. All right, so now I will talk about the microarchitecture of the chip. schematically first, and then we will turn to the physical realization. The idea is to have 5 Transmon qubits which are coupled to each other capacitively, which leads to the following interaction term in the entire Hamiltonian of the whole system. Also, these qubits are coupled to the resonators as well capacitively, and the resonators in their turn are coupled to the feed line where the readout can be performed. The qubits are in frequency domain. They're placed in a checkerboard pattern, so the interaction between them can be turned off when they are in the idling points. And the resonators are located above them in frequency, and also the couplings to the resonators should be adjusted because as the tuning between the resonators and the qubit grows, then the effective dispersive shift will be smaller. So this is a quite complicated device to design, actually, because we need to make electromagnetic simulations in special packages, which can take long, and so there is a special PhD student who is occupied only with designing the chips with more and more qubits. So when you want to make the chip, you need first the technological blueprints for the design, the integrated circuit design. Here is the view of the whole chip. It's 10 by 10 millimeters. There are 12 control lines. So these 2 are for the readout, and the other 10 ones are for the qubit control. So 2 lines per qubit, and 1 line is for XY gates, so the rotations of the block sphere. And the other the other line is for flux tuning the qubit frequency using the squid. So here is the qubit resonator block magnified, and the qubit itself. So the island, the superconducting island, is formed in the cross shape. To facilitate the connection between the qubits and the resonators and the control lines. These are the scanning electron microscope images of the resulting device. You can see here also the light, the rectangles. These are actually the air bridges which connect the ground plane on the sides of the coplanar waveguides to ensure the uniformity of the electric potential on the ground plane, because when the bridges are removed, the chips do not work. They are necessary part of the design.
How do you do them? Make them?
This is a photolithography process. You make a really thick layer of photoresist, then you expose it, then you bake it, so it becomes from a rectangular shape, it becomes more like oval shapes, and then you make the evaporation, and the bridge is formed because due to the shape of the resist, which is left. But it's I'm not a specialist in fabrication process, but that's how
it's made after at the second step after all the
yes, it's made in the last step. Yes.
There are many steps actually.
And fortunately, this does not deteriorate the qubits. So this is what we have checked. Okay, and the squid, the Josephson junctions are located here. They are very small. So we have an asymmetric squid, so the qubit frequency is tuned in a certain range, which we wanted to be tuned in. So then you need to connect the qubit to the experimental equipment, and this is equivalent to packaging of the usual semiconductor chips, because of course when you have seen the usual processor, it is the chip which is mounted on some kind of printed circuit board, which have a lot of connectors at the bottom, like a thousand of them, and then you just plug it into the motherboard and it works. But for the chip, the digital chip producers, the situation is a bit less complex than ours, because we need to be sure that analog signals pass through all the connections without any distortions, because we don't have the advantages of digital logic. And so the design of such kind of packages is a difficult task as well, and it requires a lot of electromagnetic simulations. And when you have more and more connectors, it becomes also more. Okay, so here is the picture of the lowest 20 milli K stage of the bridge. But now currently it's 12. I think it may be different depending on how much the load is on the bridge, how much wiring is done. So the devices are put under the magnetic shields, which are made from fiber material with very high mu. Okay, so also we use microwave isolators and a lot of attenuation and filtering to ensure that no radiation, infrared or just radiation microwave from higher stages goes into the circuit. And all the connections inside the bridge are done using the coaxial cables. Oleg has already mentioned briefly the devices that we use in our lab. So maybe I will skip the slide. Maybe I will make a bit more. I will say a bit more about the fast digital electronics that we have here. We use the PXI chassis, which is a platform that allows to get rid of the box format devices. They become really compact and can be put into the slots. And for example, this chassis incorporates, I think, 5 microwave generators, 4 AWGs, and an ADC. So this is a very powerful platform to make a scalable quantum device. And you can see that there is a lot of cables, and this is also a problem of scaling. But I think for hundreds of qubits, it will be still manageable. All right. So the experimental results are presented from measurements of the circuit from the 11th series. We have spent the previous year, I think, in the beginning of this one, developing different variants of the design, because we had to. And this was the first, the sample that was for us satisfying. And here the spectra of the readout resonators are presented. The resonators are following when you tune the magnetic flux through the qubit. The resonators, due to the dispersive coupling, they follow the qubits a little bit, so you can see a small periodic changes of the resonator frequency, and you can also measure the crosstalks between the lines, the flux control lines of each qubit with the other ones, and the diagonal of this matrix shows that the crosstalks are really small, because large oscillations are only visible on the diagonal part. Next, we were working with 4 qubits of this chip. And here the spectra are presented. You can see that the reproducibility of the qubits is really high. It's lower than 5% error in frequencies after the fabrication. It's pretty good for our technology, and it's on par with the world. The red arrows show the idling points of the qubits, which we have used in the test experiment that I will be talking about further. So in these idling points, we have measured the idling, or we have measured the decay and the transverse decay, the coherence of the non-diagonal elements of the density matrix of the qubits, and we observe the T1s up to 12 microseconds and T2s up to 8.5 microseconds. So it's was a great win for us, and I think we will improve these results further.
But I have a question. So, is it just random fluctuations which cause this dramatic difference, 6 and 12?
Yes. So there's still no microscopic model for the two-level defects that coupled with the qubits and cause the energy loss. So you can't. So since it's microscopic, you can control it beforehand. You just fabricate it, and then you observe on the chip. And actually, it may depend on the frequency of the qubit. So you can tune the qubits in frequency, and you will see that it will have different T1 times in different points, and they can change quite rapidly. And even you can observe coherent oscillations with the defect in the spectrum. So yes, this is no one knows how to control that. And if you look at the results of the top groups, they will still have these deviations. For T2, for the transverse decay, is actually less severe because this one is lower because it is located outside the sweet spot. But the other ones are quite close. So I will also give a brief description of the two-qubit gate that we use, the ITMO gate. The algorithm is to bring the qubits shortly into resonance with each other and allow them to exchange energy for some time, and then again tune them back to the idling points. So it is shown here in this graph. So the qubit, the orange one, is tuned down in frequency, comes into the resonance with the blue one. Here the interaction occurs, and then it is returned back to its idling position. So here in this graph, the interaction time is shown on the y-axis, and the target phase, this red line, is shown on the x-axis. And you can see that right in the resonance, there are oscillations. If you look at the section of them, these are the cosine and sine wave for the first and the second qubit respectively. So if you break the interaction at this point, this is a square root of an ITMO gate, or if you break the interaction at I think it's half pi over g, you will get an ITMO gate. So the energy is transferred, and there is also an additional phase which will be visible if you consider the transfer of superposed states. The pulse sequence that realizes the state transfer from the first qubit to the fourth one is shown here. The first qubit is excited by a pi pulse. Then the second qubit is by applying rectangular pulses on the flux bias line. It is tuned into resonance with the first qubit first, and then with the third one, and then the third one and the fourth one are tuned into resonance simultaneously, and then read out as before. Let's break this algorithm first. into several steps. So first we do, as a check, we do pi pulses on each of the qubits, and we also vary the amplitude of the pi pulse and look how the probabilities are changing by reading out each qubit by its own resonator. So the results are presented here. So we have excited the first qubit with varying amplitude, with the second one, the third one, and the fourth one. And the qubit that is read out is the same as the excited one. And we can see that, well, the probability is actually inferred from the measurement. You measure the complex transmission parameter, and then looking at the Rabi oscillations, you can say what complex transmission corresponds to 0 state and what to the 1 state. And we can see that when this test is done in the algorithm, for some reason, the imaginary part of the signal is biased. And we had to correct it in software. And well, actually, unfortunately, we didn't have yet time to find out why this happened. We will look into this in, I think, in the future again.
But so this is a probability amplitude, right?
This is this is just, I think, the mean value of the projector to the 1 state.
Okay, but still you have real and imaginary part.
It should be the same actually. So this the orange curves should match with the blue one.
Yeah, maybe my misunderstanding. But if you take an observable, let's say, and calculate the expectations, isn't it always?
Yeah, I shouldn't show. It's a technical detail. Yes, they should follow each other. Yes, but for some reason they don't.
I'm sorry, but why become more than one of those?
It's noise. It's noise, probably. Yeah. So it's the readout of the qubits is also a big deal. We are working on that as well. Now we have a Josephson parametric amplifier because we didn't have it when we were doing these experiments. Now we will be able to look into this problem in more detail. I'm just showing you that so that you know that there are some problems that are not evident in the first place. Okay, so the first now we will look at the results of the transfer between the first qubit and the third one. The numbers 1 and 2 corresponds to these graphs. So this is transfer from the first qubit to the second one, and this is transfer from the second one to the third one. In both these pictures, measured is the second qubit. So it starts from a blue color, that means that it's not excited. Then after, if we tune the Z pulse amplitude on the flux bias line and the interaction duration, then at some point it becomes excited, which is the probability here is measured by using these plots that I have shown before, calibrated by a simple pi pulse on certain qubit. And then we measure it again, but at this point of the algorithm, this one, the first one was here, and now here. And we observe that it goes from the excited state, yellow, to the ground state, which is shown in blue. So this part of the experiment works nearly perfectly. We didn't do benchmarking, but looking just at the probabilities, we see that it gets fully depopulated. And the first one and the second one and the third one is fully populated. Okay, so now the final part of the interaction goes here. This is done in a different way. So now both qubits are tuned, and this leads due to the distortions in the pulse of the nature which is not really evident to us yet. And the transfer gets less, well, the fidelity of the transfer gets lower. It's around 90%, but still it may be done.
So, so do I understand correctly that you consider the process of bringing a photon from the left edge of this 4-qubit array to the right edge? Yes. Then what you check is how efficient this is done.
Yes.
Roughly speaking.
by looking into probabilities. So it can be done better, of course, but we didn't do it due to the lack of time. Oh, actually, I think this is the last slide. So we have developed a fabrication method to develop to make qubits which are quite reproducible in frequency and with satisfying coherence times that allows us to perform simple algorithms on the device. We have performed the simplest parameterized 4-qubit algorithm, and currently we're trying to improve the fidelity of 2-qubit gates to be able to perform the machine learning that I was starting with. So that's the end. Thank you for your attention, and I can now answer your questions.
Thanks, Gleb. Now we can take a couple of questions and then we'll go for lunch. So my question actually is related to the very beginning of your talk, where you mentioned that since error correction is quite tricky nowadays, people look at error-prone quantum circuits, trying to make sure that they are not so sensitive to some disorders.
Yes.
So can you tell us briefly what are the main strategies how to make such error-prone circuits?
Well, actually, when you look at the examples of quantum deep learning in the simplest case, when we don't use, for example, this part, you measure the averages of for example, sigma z polymetrics, and you look only if the average value is above 0 or below it, for example. So the discretization happens there. And well, we tested that even with the coherence, this approach can lead to well, satisfying classification accuracies. And yeah, that's it. So,
so instead of measuring some continuous variable, you look whether the value is above or below 0.5.
Yes, and it happens in the end of the algorithm. So if any coherence is present there, then you will still be able to measure something.
Thank you.
Is it possible to see, or maybe we've seen in your system something like superradiance effects or subradiance effects? Can you compare?
In this one, I don't think, because we don't have a common resonator, right? They are coupled to, but
but they have tie binding couple, no?
Yes, but where they should radiate into.
Okay, so what's their lifetime? So is it finite?
If so, am I understanding this correctly? So the superradiance is in the decay model when you have several qubits coupled to a resonator, and if they are
not necessarily. There might not be a resonator. There's a lifetime in your qubit, right? It's radiative, I suppose. So now, if you prepare several of them in special state, yes, it's not radiative.
Yeah,
it's a couple of lines. It's a purpose to make them long lived. So it's different from the quantum optical experiments.
Okay, so maybe that's what I was.
So they should be all coupled to the same reservoir, right? Otherwise, it won't work.
Or even one, when none of them is coupled.
Okay, but I mean, if there's, for example, some defect, if we know that the qubits radiate into the substrate, if there's a common defect that they couple to, but it still won't be possible.
You need to measure radiation somehow.
Yeah.
Yeah, so here there are qubits, so they're on intent, are isolated to store the excitation there until we read it.
Yeah,
but I should have people were doing some experiments with qubits placed in the waveguide. This is Josephson group in Germany. Lately, that would be with such a product.
but I didn't know if they succeeded yet to show the superradiance.
No, not superradiance. They were a bit simple things. Step by step.
I think that there was some in a waveguide, not.
I'm not sure about
superradiance, but
maybe they didn't even target simple things.
Well, it's an interesting topic, and I think it would be possible to realize this kind of experiment with superconducting systems. Maybe it's the best platform.
Yes, obviously, if you want to discuss.
Yeah.
So colleagues, any other questions? If not, nothing in Zoom, good. So I suggest to conclude, and then we have some time during the day for some more questions from our speakers. So they will be available in service room and taking some excursions in the department. So do not hesitate to contact me or them directly in case if you have any questions. So thanks again, Gleb.